Begin the summary lecture 11 in week 11. From the last week, you are learning about the quantum mechanics. Just for your reminder, let me repeat this notes for the quantum mechanics. So it's not like the classical physics, the macro scale. So now we are exploring atomic scale nature. Especially we are interested in the behavior of electron and atoms. The experiment results contradict to the classical physics. So we do the experiment in the atomic scale. Then what we found, it cannot be explained by this classical physics. So we are trying to develop the new model to explain those new observations, and then the following experiment verify the suggested model or theory. And then so far they are working well. So now we are using those theory for our real life. Okay, so in the atomic scale, there's something we cannot explain using classical physics. And also there's the issue whether light or electrons are wave or particle. So they have the duality of the wave and the particles. So regarding these two issues, you learned about the black body radiation and photoelectric effect in the last week. Then this week you learned about the spectrum from the atom, especially from hydrogen. So we can observe the sharp spectrum from the specific atoms, and the Compton effect and wave property of electron. Okay, so there are 4 parts in this week 11 Compton effect. So this experiment tell you that light is particle, and the wave particle duality, so it is suggested by the de Broglie. Then in here the particle is like wave. So yes, especially electron is considered as particle, but at some situation the electron is behave like wave. And then this experiment has been done in the open space without any constraint. But so since we did, hello, any questions? All right, thank you. So since we developed this new model from the experiment, we adapted the new constraint in that model. So the most simple the problem is the particle in one-dimensional box. So we added the boundary condition of the electron, moving electron. Then yes, we developed the model of the standing wave of the electron in this confined one-dimensional box. Then yes, I'm gonna handle the atomic spectrum from the. Then this behavior was explained by Bohr's hydrogen model. All right, let's begin the Compton effect. So in this experiment, at first we shine the light to the material, for example, graphite, which is quite similar with photoelectric effect, but it gives the different behavior because the photon energy is much stronger than the light used in the photoelectric effect. Okay, so we shine X-ray. X-ray means it has a much shorter wavelength, then it has a high photon energy. Then when you detect the light pass through this graphite, then if the degree of the angle is 0, then you can observe only the single wavelength, which is same with the wavelength of the incident photon. And as you increase the angle, so we start to observe the separation of the two peaks. So there is the lambda 0. This is the wavelength of the incident photon, and we start to have another peak. Let's say this is the lambda prime. Then as you increase the angle, this lambda 0 and lambda prime is separated more as you increase the angle, as you can see here. Then this behavior is explained by this simple mathematical derivation. So it is called as a Compton-Shift equation. Why do we have this behavior? Because light behaves as a particle, and this light, which is photon, when this photon is incident to the material, this photon has a collision with the electron around the atom. Then this light is scattered, so as you change the angle of the observation, you can observe the separation of the peak of the two wavelengths of the light. So in classical physics, if the light is wave, then this scattered light should have a broad distribution instead of the separation of two distinctive peak of the two wavelengths. Okay, then let's think about the modeling from this experiment, Compton effect. At first, we have incident photon. Its wavelength is lambda 0. And you can define the momentum of the photon and energy of the photon. The momentum is h over lambda 0, and energy is hc over lambda 0. This is the momentum and energy of the incident photon. Then, now we consider this light as a particle, which is photon. So once this incident photon hit the electron, so like the billiard ball hit each other. Then once they have a collision, they are separated like this, right? So electron goes this way, and the scattered photon incident this way. Then they form certain angle. So let's say the angle of the scattered photon is theta, and the propagating angle of the electron is phi right here. Then now in this model, we need to consider the conservation of the momentum and also energy. So yeah, we need to consider the two conservations. The one is momentum along x-axis, along y-axis. Another one is energy conservation. So we have the energy of the incident photon. So the sum of the scattered photon energy and kinetic energy of the electron should be equals to the photon energy of the incident photon right here. So at first you can define this relationship according to the energy conservation. For the momentum conservation, you can have two equations. At first, along x-axis, before collision, we had the momentum of the incident photon, which is h over lambda 0. So, and after collision, this scattered photon has x component of the momentum, and this scattered electron also has the x component of the momentum. So the momentum of the scattered photon is h over lambda prime. Then for the x component, you multiply cosine theta. Okay, let's say the momentum of the electron is Pe, then the x component of it is P cosine V. So this is the one equation for the momentum conservation along the x-axis. Along the y-axis, so the incident photon doesn't have the y-axis component of the momentum. So the y-axis component of the momentum of scattered photon is equals to the y component of the momentum of this electron. So you can have this equation. So considering these three equations, and also actually this is not the coverage of this course, but if you consider the theory of the relativity, then eventually you can derive this Compton-Shift equation. So the lambda prime minus lambda 0, which is delta lambda, the shift of the wavelength, equals to the constant times 1 minus cosine theta. So I uploaded another the PPT slide as a PDF file. So if you are interested in how you can derive this Compton-Shift equation from these two conservation, then yes, please take a look at PDF file, download it, and take a look PDF file. So then you can follow how you can derive this Compton-Shift equation. Okay, then let me ask you one simple question. Question is, which of the following is not considered for Compton scattering? Alright, it seems that most of you are following very well. Okay, so in this Compton effect, as I explained here, we need to consider the momentum conservation of the scattered photon and scattered electron. Next, we need to consider the energy conservation. So the energy of the incident photon should be equal to the energy of scattered photon and kinetic energy of the electron. And then you can use this Compton-Shift equation. So wavelength shift after scattering. But most of the time we don't consider the force balance. So the answer is C. Okay, then let's move on to the sample example question. So this is the past year exam in academic year 18-19. In Compton scattering, an incident photon is scattered by a free electron initially at rest, such that the scattered photon propagates in a direction perpendicular to that of the scattered electron, as shown in figure below. So the electron was here. Then we had an incident photon right here. Then once they have a collision, electron goes this way and the scattered photon goes this way. Then eventually their angle is right angle, 90 degree. The scattering angle of the scattered photon is theta. So this angle is theta. That means the angle of the electron propagation is 90 minus theta. Show that the wavelength of the scattered photon is fixed at lambda prime is 2.43 picometer, irrespective of theta. Okay, so in this Compton scattering, you need to consider the conservation of the momentum of the electron and photon in here. Okay, at first, you need to think about the momentum conservation along the vertical direction. So usually we define this vertical direction as a y-axis. Second, you need to consider the momentum conservation along the horizontal direction. And next, you're going to use the formula of the wavelength shift. So this Compton shift equation. Okay, let's think about the momentum conservation along the vertical direction. We have, so in here you need to consider the y component of the scattered electron. So it is PE, let's say PE is the momentum of the electron, times sine 90 degree minus theta. This is the y component, vertical component of the momentum of the electron. Next, the y component of the scattered photon is h over lambda prime times sine theta. So from here you can define the momentum of the electron. PE equals h over lambda prime sine theta divided by this sine 90 degree minus theta. So this sine 90 minus theta is cosine theta. So this momentum of the electron is h over lambda prime times tangent theta. Okay, from vertical direction momentum conservation, you can define the momentum of the electron as a function of lambda prime and theta. Okay, then let's think about the horizontal direction. So in horizontal direction, the initial momentum of the incident photon is h over lambda 0. Then it is equals to the sum of the x component of the momentum of the scattered photon and electron. What is the x component of the scattered photon? H over lambda prime times cosine theta. And the second term is x component of the electron momentum. PE times cosine 90 degree minus theta. Okay, so in the next line, we keep the first term. Then second term, you can bring this, the momentum of the electron as a function of theta. We found this in the previous slide. So this one goes to here. Then cosine 90 minus theta is sine theta. So we have sine theta here. Alright, then this tangent theta times sine theta is sine square over cosine. So if you make a summation of them, it is h over lambda prime cosine square plus sine square divided by cosine theta. So it is h over lambda prime divided by cosine theta. Okay, this term is equals to h lambda 0. H is cancelled out, so you can define lambda 0 right here. Lambda 0 equals lambda prime cosine theta. Okay, then now let's use the Compton shift equation. Lambda prime minus lambda 0 equals the Compton constant times 1 minus cosine theta. So this is the given equation, right? Then this lambda 0, we already defined lambda 0 right here. Lambda 0 equals lambda prime cosine theta. So if you apply this to here, this term, the left hand side is lambda prime times 1 minus cosine theta equals to this term we keep here. Then you can notice that 1 minus cosine theta is cancelled out. So lambda prime is Compton constant h over mc. So if you apply the constant, then you can calculate lambda prime. So the answer is 2.43 picometer. It is very interesting. So when this angle between the electron and lambda prime, the scattered photon, keep the 90 degree, then we can determine the lambda prime regardless the wavelength of the photon, incident photon. Okay, then let's move on to the next question. This is also the past year exam question. An incident photon of wavelength lambda 0 is scattered by a free electron initially at rest, such that the scattering angle of the scattered electron theta equals that of the scattered photon, as shown below. So we have incident photon and its wavelength is lambda 0. And the electron is scattered and the photon is scattered as also opposite. So this is the scattered photon and this is the scattered electron. Then their angle is same, both are theta. Using the concept of the momentum conservation, show that the momentum value of the scattered electron Pe can be determined by the following equation. Yes, we want to define the momentum of the electron as a function of the wavelengths lambda 0 and theta. Then we need to use the momentum conservation along the vertical direction, and we can use the formula of the wavelength shift, the Compton shift equation. Okay, at first, let's consider the momentum conservation along the vertical direction. Okay, in here, so the vertical component of the incident photon is 0. Then the vertical component of the electron momentum is Pe times sine theta, because this angle is theta. Then another one, the scattered photon has a momentum of P photon. Let's say this is P prime, and the vertical component is sine theta. Okay, in here, so you can find that the momentum of the electron, since the sine theta components are cancelled out, So PE, the momentum of the electron, equals to the momentum of the scattered photon. And what is the momentum of the scattered photon? Which is h over lambda prime. Okay, so we define the momentum of the electron as a function of the lambda prime in here. Then let's use the Compton shift equation. Lambda prime minus lambda 0 equals to the Compton constant times 1 minus cosine theta. So the lambda prime is, so we move this lambda 0 term to the right hand side. So lambda prime is lambda 0 plus the constant times 1 minus cosine theta. Okay, then now you can apply this to this equation to define the momentum of the electron. Okay, so if you apply this to this at the denominator, then the momentum of the electron is h over this lambda prime term. So yeah, as recasted in the question, we define the momentum of the electron right here. Okay, the next question. A 0.5 mega electron volt photon scatters of a free electron that is initially at rest, such the scattering angle of the scattered photon is 30 degrees. So yes, we have a resting electron here, then incident photon has collision with it. Then electron is scattered along this direction, the angle is B. Then photon is scattered along this direction. Then this theta is 30 degrees. This is the given in the question. Alright, determine number 1, the energy and momentum of the scattered photon. Okay, if you want to define energy and momentum of the photon, you need to find wavelength of it. If you know the wavelength of the photon, you can define energy and the momentum. hc over lambda and h over lambda. You can use that formula. Okay, to find the wavelength of the scattered photon, let's use this Compton shift equation. Lambda prime minus lambda 0 equals the constant times 1 minus cosine theta. So lambda prime is lambda 0 plus constant times 1 minus cosine theta. Okay, then how can you define lambda 0? What clue we can use in the question? We have the photon, the energy of the incident photon, which is 0.5 mega electron volt. So if you know the photon energy, then you can define the wavelength of the photon right here. So lambda 0 is hc over the photon energy, E0. So you can apply this to here. Then let's put all the given constant. This is h, the Planck constant, speed of the light, and this is the photon energy, energy of the incident photon, 0.5 mega electron volt. And notice that, so in this equation we want to use the unit of joule. So this electron volt has to be converted to the joule. So we multiply charge of the electron. This is the first term. In the second term, we use same Planck constant, and this is the effective mass of electron. This is the speed of the light. Then notice that we already have the angle of theta, which is 30 degrees. Then if you calculate them, you can have lambda prime, which is 2.8 10 to the negative 12 meter. So it is 2.8 picometer. Alright, now we got the wavelengths of the scattered photon. Then we can calculate the energy and the momentum of them. How do you calculate the energy of the scattered photon? E prime is hc over lambda prime. Then the wavelength is 2.8 picometer right here. So the energy of the scattered photon is 0.44 mega electron volt. What about momentum? Momentum P prime is h over lambda prime. So it is 2.36 10 to the negative 22 kilogram meter per second. Okay, so we got the energy and momentum of the scattered photon. Then next, we want to calculate the kinetic energy of the scattered electron. Then now we can use the energy conservation. So the kinetic energy of the electron Ek is energy of the incident photon minus energy of the scattered photon. E0 minus E prime. So what is the incident energy? 0.5 mega electron volt, and the energy of the scattered photon is 0.44 mega electron volt. So the kinetic energy of the electron is 0.06 mega electron volt. And number 3, scattering angle of the scattered electron. So we want to calculate B right here. Then we need to use the momentum conservation along the x-axis and y-axis. Let's consider the x-axis first. Along the x-axis, the momentum of the incident photon is h over lambda 0. Then this momentum has the two components. X component of the momentum of electron and x component of the momentum of scattered photon. So PE, let's say PE is the momentum of electron. So x component is PE cosine B. Then second term is h over lambda prime. This is the momentum of the scattered photon for x component multiply cosine theta. Okay, in here, the PE cosine B, this term, equals to h over lambda 0 minus h over lambda prime cosine theta. Okay, then let's move on to the y component. In y component, the PE sine B, the y component of the momentum of electron, equals to the y component of the momentum of scattered photon, h over lambda prime sine theta. Okay, so now you have two equations right here, and in the question we want to calculate this B, scattering angle. Then you can divide these two equations each other. Then you can have tangent B, which is the sine B divided by cosine B. Then it is tangent B. The P is cancelled out. Then at the numerator we have this term h over lambda prime sine theta. At the denominator we have this term h over lambda 0 minus h over lambda prime cosine theta. Okay, and then so this HC, okay, multiply the speed of the light at each side, each term. Then this hc over lambda prime is E prime, the energy of the scattered photon, and EC over lambda 0 is the energy of the incident photon, E0. Then you can simplify, you can make this equation simple, as you can see here. So E prime is 0.44 mega electron volt, and this theta is 30 degrees, so sine theta is 0.5. E0 is 0.5 mega electron volt. E prime is 0.44, cosine theta is 0.866. So tangent phi is 1.85. So phi is 61.6 degree. Okay, so I gave you the 3 example question about the Compton shift. Then as you can notice, we always consider the momentum conservation along the x-axis and y-axis, and energy conservation, and if necessary, you need to use the Compton shift equation. Alright, then let's move on to the atomic spectra. So I believe all of you already completed the experiments lab session in this course. So you use the mercury lamp, and so we used to use the 3 kind of lamp, but in this semester we decrease it 2. So yeah, you use the helium and incandescent lamp, right? Then especially when you use the helium lamp, you may observe this sharp spectrum of the visible light. So it was found in the hydrogen lamp first. So it was found by the Balmer. So that's why this visible, the spectrum of the visible light, the 4 wavelengths, are called as Balmer's series. And then, yeah, he could define the wavelengths of each spectrum. Then he found this mathematical relationship. 1 over lambda equals to a certain constant times 1 over 2 square minus 1 over n square. And n is varied from 3 to 6. Okay, then after that, Lyman observed the UV light range. Then he found another spectrum at the UV range. Then he defined the wavelengths of that spectrum. Then he could define this equation, very similar to Balmer series, but this denominator is 1 instead of 2. So this equation is 1 over 1 square minus 1 over n square. Then we could observe the specific spectrum at the infrared light as well. Then this Paschen series uses 3 at here. Then Brackett series uses 4 at this equation. Alright, these equations are very similar. Then interesting is, actually they didn't suggest any reasonable model of why we have this specific spectrum. They just derive this mathematical equation fitting to their observation, measurement. So there's only mathematical equations, there's no theoretical explanation about it. And then Bohr suggested atomic model with these assumptions. Then he could explain why we have such specific spectrums. And then he could derive these equations. Universal equation can be applied to the 4 series. Okay, in Bohr's model, actually this is the most well-known and the straightforward atomic model for even for the normal people, not special, haven't run this quantum mechanics. So basically, it is like a solar system. We have the proton at the center of the atom, and the electrons are orbiting around the proton. So proton has positive charge and the electron has negative charge. So they have attractive force. Then, in this solar system, we have attractive force between Sun and Earth and other planet, the gravity force. Then since we are maintaining certain velocity, rotate angular velocity, we have a centripetal force. So these two forces are making balance each other, then we can maintain certain orbit. So in his model, it is like a solar system. So proton has positive charge, electron has negative charge. They have a Coulombic attractive force. But electron has a certain angular velocity, so it has a centripetal force. So there is a force balance in the certain the orbit of the electron. Okay, first assumption, to summary, first assumption is electron moves in a circular orbit around the proton. Second, only certain orbits are stable. So this orbit is not continuous. So there is only certain discrete orbit. A photon is emitted when an electron jumps from the higher energetic into initial orbit to the low energy orbit. So each orbit has a certain state energy value, the potential energy. Then once electron has a transition, it releases the energy as a form of photon. So on the allowed orbit, the electron's orbital angular momentum about the nucleus is an integral multiple of the h equals h over 2 pi. So eventually we can have this equation. The delta E, the energy difference, is equals to the photon energy emitted, HF or HC over lambda. Then he could derive this the energy equation for the integer value of n right here, considering the Coulombic attraction and the centripetal force of the electron when it is orbiting a certain trajectory. Okay, from these two equations, we could define the wavelength of the photon. 1 over lambda equals to the delta E over HC. Then you can apply these equations of the energy of electron to these two terms. Okay, then you can have these equations. So 1 over lambda equals the constant times 1 over nf squared minus 1 over ni squared. So this equation is a general equation of the previous mathematical definition for the spectrum of the hydrogen. So this Balmer series is for the Ni is 2. And this Riemann series for n equals 1. And this series for n equals 3 and 4. So based on this Bohr's model, we can explain how we can have these 4 specific series of the spectrum: the Riemann series, Balmer series, Paschen series, and Brackett series. So there is a discrete energy level, and from n equals 1 to infinity. So when the electron is relaxed to the ground state, which is n equals 1, we have the Riemann series. So this gap represents delta E, and it determines the wavelength of the emitted light. So Balmer series is about the visible light. Then it is caused when the electron is relaxed to the second energy level, n equals 2. So this Bose model could explain this hydrogen spectrum right here. Okay, then let's try one example question. The emission spectrum of hydrogen in visible light range shows 4 sharp colorful lines at the wavelengths of 0.656, 0.486, 0.434, and 0.410 micrometer respectively. Number 1, explain the origin of the emission spectrum using the Bose model. Okay, as I explained it in the previous slide, Bose model has an orbiting electron, and they have a discrete energy level for the corresponding orbit of the electron. Then each orbit is determined by the integers n, as you can see here. Then this is the energy level of each orbit. The ground state is when n equals 1. The next level is when n equals 2. N is increased to the infinity. Okay, then in this visible light range, there is the transition, relaxation of the electron to the second energy level, n equals 2. So we all know that the longer wavelength has a smaller photon energy. So when the electron is relaxed from 3 to 2, it emits this longest wavelength. And when electron is relaxed from 6 to 2, it emits the shortest wavelength among these 4, which is 410 nanometer. Okay. Then second question, number 2. Determine the energy between the level that involved in the emission process. Okay. So using the equation defined by Bohr's model, we can calculate the wavelengths, emitted wavelengths. Okay, for 656 nanometer line, the delta E32 is this gap, the red one, from 3 to 2. This E3 minus E2 is equals to HC over lambda. Then you can calculate delta E. So H is Planck constant. This is the speed of light. Lambda is 656 nanometer right here. So this is 3.1 10 to the negative 19 joule. If it is divided by electron, then you can convert unit. So it is 1.9 electron volt. The other calculations are same. For 486 nanometer line, it is this green line from 4 to 2. So the lambda is 400. Oh, sorry, this is typo, 86 nanometer, and it is 2.6 electron volt. The third one, 434 nanometer. This is this blue one, from 5 to 2. So it is 2.9 electron volt. The shortest wavelength is 410 nanometer, the purple one. From 6 to 2, its energy is 3.0 electron volt. Okay, So if you have any question, feel free to type the text or call me after you unmute your mic. Okay, then let's move on to the next topic, wave-particle duality. Okay, in the last week, we learned that light is wave, but also light is behave as a particle, which is photon. So for photon, we could define the photon energy. E is hf, and its momentum is h over lambda. Then for matter particles, we can consider it as a wave instead of particle. Okay, then let's say this particle's energy is E. Then if it is wave, then we can also use the same equation, hf. In the meantime, if the particle is traveling with certain velocity, you can define its kinetic energy. So which is 1 over 2 mv squared. Okay, so from this equation, the lambda is h over p, like this photon. Then p is mv. So you can define the wavelength of the traveling particle, as you can see here, h over mv. That was the theory suggested by de Broglie. Then Young's double slit experiment actually proved that this particle is behaving like a wave, especially electron. So he did the experiment, as you can see here. So he made a double slit. There's a two slit right here. Then he shoot the electron. So electron has a certain velocity, and when electron pass through these two slits, if the electron is particle, so when you detect the electron at here after certain distance, so you can have this distribution of the electron. So this distribution P1 from slit 1, and this another distribution P2 is from slit 2. So that was his expectation, assuming electron is particle. However, the actual result was different. So when he measured the population of the electron, he could observe this periodic pattern. It is similar with the constructive and destructive pattern interference of the light. So you learned about this behavior in week 3 or 4, the first part of this course, right? Okay, so this electron also has this constructive and destructive interference, as you can see here, when he tested the double slit experiment. So from this experiment, he could prove that electron has wave-like behavior as well, as suggested by de Broglie. Okay, then this duality, the wave-particle duality, also supports the Bohr's model. Then it can support then why this electron has discreted orbit, not continuous. Okay, so let me remind you the assumption of Bohr's model. At first, the angular momentum is angular momentum of the electron in this orbit is m times Planck constant, right here. So mvr equals n h over 2 pi. Then this 2 pi r, so you move this 2 pi term to here and move mv term to here. So 2 pi r equals n h over mv. Okay, then in here let's bring the wave particle duality right here. So in here lambda is h over the momentum of the particle. What is the momentum of the particle? Which is mv. Now you can bring this term to here, h over mv. Then this 2 pi r equals n times lambda e, the wavelength of the electron. Okay, what is 2 pi r? 2 pi r is circumference of the circle, right? So, in this circumference, we can have the wavelength times integer of the electron. So that means, let's imagine this is the circle. I know it's not looks like circle, but yes, this is okay. This is the orbit of the electron. Then, if you cut it, then the length of this string is going to be 2 pi r. Then, if n is 1, then this string has a single mode of the vibration like this. If n is 2, this string will have the second mode vibration. So node is at the center of the string, then you have a certain vibration right here and another vibration right here. So yeah, actually it's hard to demonstrate. So this is the first mode. Then if I rotate very fast, I hope that I can see the second mode, but cannot make it. Then if you increase this integer n, then you can have the third mode, fourth mode, fifth mode. Then again, this is the circle, right? Then you can have this behavior of the electron at each orbit. Of course, if n is 1, then it will draw circular trajectory. If n is 2, okay, please follow me carefully. Let's start from here. Then we have one wave right here. This is 1 and 2. So we have 2 wavelengths in this circumference when n is 2. When n is 3, we have 3 wavelengths starting from here. 1, 2, 3. If n is 5, then we have 5 wavelengths. Okay, so this wave particle duality explains that electron can have this standing wave in the given orbit. So that's why they have this discrete orbit depending on the n value of the integer. Okay, so then let me show you one example question. Electron diffraction patterns from a crystal can be used to determine the crystal lattice structure. In order to create clear electron diffraction patterns, incident electrons should have a de Broglie wavelength comparable to the distance between adjacent atoms in the crystal. Typically about 0.1 nanometer. What is the kinetic energy of the incident electron? Actually, this question is very long, but the solution itself is not very complicated. Okay, so let me explain about the electron diffraction pattern first. So we have a very thin specimen, and we shoot the electron. Then by the electron diffraction with the atoms in the crystal, it gives a certain specific patterns right here. But if the kinetic energy of the electron is not strong enough, its wavelength is too long, then we cannot have a good resolution of this diffraction pattern. So to get the fine diffraction pattern, we increase the kinetic energy of the electron. Then its wavelength is decreased, then we can have a better resolution. Okay, in this question, the required wavelength of the particle is 0.1 nanometer. Then we need to calculate kinetic energy of it. Okay, so when the de Broglie wavelength is 0.1 nanometer, the momentum of the particle is h over lambda. Then what is kinetic energy? Kinetic energy is p square momentum square divided by 2m. So, okay, in here, p square is h square over lambda square right here. And h is Planck constant, m is mass of electron, lambda is 0.1 nanometer. So the kinetic energy of electron is 150 electron volt. Okay, this is how you can utilize use the de Broglie wavelength to define the kinetic energy of the particle. And in opposite way, if you have the kinetic energy of the particle or momentum, then you can define the de Broglie wavelength of the particle. Okay, the last topic, a particle in one-dimensional box. So in the previous topic, so we considered the electron traveling in the free surface without any constraint. There's no boundary conditions. Then question is, okay, now we developed many kind of models and derived the mathematical equations considering without constraint. Then we had a question, what if there is a boundary condition for wave of a particle? Then we started from simple model, the one-dimensional box. So we have the constraint here, then their distance is L. Then electron is moving around between these two boundaries. Then we can define the wave function considering the electron has standing waves. First mode, second mode, third mode. Then you can define the probability of the existence of the particle, electron in this case, and the total probability when the range is from negative infinity to infinity, then that value has to be 1. To calculate the probability of the existence of electron for the specific intervals, then you can do the integration from A to B. Okay, then let's try two more example questions. A free electron has a wave function where x is in meters. So we define the wave function of the electron as you can see here. Then number 1, find de Broglie wavelength. Okay, if you have a wave and if you can find wave number, you can define the wavelength of it. Okay, so we have a wave function right here. So it is decomposed to A cosine plus AI cosine. I sine. Then inside of cosine and sine, we have this term, the 5 10 to the 10x. Okay, let's make it simple. It is a cosine kx plus ai sine kx. And k is the wave number. Then you can define lambda. So wave number k is 2 pi over lambda. And this k is 5 times 10 to the 10 per meter. Okay, then wavelength is 2 pi over k, so it is 1.26 10 to the negative 10 meter. Okay, this is how to find the de Broglie wavelength from the wave function. Okay, next, find momentum. Now we have the de Broglie wavelength. If you have a wavelength, then you can define momentum and kinetic energy or photon energy for the light. So the electron momentum P is h over lambda, and lambda is here. So momentum is 5.25 10 to the negative 24 kilogram meter per second. Last one, kinetic energy. Kinetic energy is P square over 2m, and P is here. Or you can use this Planck constant and the lambda as well. Then put the numbers. Then you can calculate the kinetic energy of electron, 95 electron volt. Okay, next question. An electron is trapped at the ground state of an infinitely deep quantum well with a width of 2 nanometer. So we have the two boundary, and the width is 2 nanometer. After observing a photon, the electron transits to an excited state. Given that the de Broglie wavelength of the electron at this excited state is 1 nanometer, so we have a de Broglie wavelength here. Find the quantum number of the electron at the excited state, sketch the corresponding wave function, and determine the wavelength of the incident photon. Okay, then I want you to find the answer of the first question. Okay, now we have a confined quantum well, and its width is 2 nanometer. And the wavelength is 1 nanometer. What is the quantum number in the current status? Alright, so you can use this equation. The de Broglie wavelength is 2L over N. So N is 2L over lambda. L is 2 nanometer and wavelength is 1 nanometer. So the answer is 4. Then let's sketch the corresponding wave function. So we have infinite quantum well. The length is 2 nanometer. Then you can draw these waves. when the n is 4. Okay, then let's calculate the wavelength of the incident photon. Okay, so at first this electron was at ground state, which is n equals 1. Then now it is excited to n equals 4 by the incident photon. Okay, then photon energy will be difference of the energy level between 1 and 4. So the photon energy is hc over lambda equals the constant times 4 square minus 1 square. Then lambda is 8 mcl square, this term, times speed of light c, and the 16 minus 1 is 15 right here, 15h. So the wavelength of the incident photon is 879 nanometer. Okay, this is the answer of this question. So I'm going to share this. I already shared this PPT slide, and also I'm going to share the recorded video. So if you couldn't follow this question well during this time, so please review your PPT slide and watch video again if necessary. And if you still have a question, please feel free to approach me or your tutor anytime. Alright, so this is the last question. Using the Bohr theory of the atoms, show that the speed of the electron in the nth Bohr orbit in hydrogen is given by this equation. So we want to derive this. From the Bohr theory, at first you need to consider the angular momentum mvr equals nh over 2 pi. So from here you can define r. R equals nh over 2 pi mv. Then next, let's consider the Coulombic attraction equals to centripetal force, the force balance. So this is the Coulombic attraction. The Coulombic constant times E square over R square. R is the radius of the orbit. The centripetal force is mv square over R. Okay, then R is the one R is cancelled out here, and then you can apply this to here. Then you're gonna have 2 pi mv ke square nh equals to mv square. Then mass of electron is cancelled out. The v is cancelled out here. So eventually you can define v. V equals 2 pi ke square divided by nh. So you derive this equation. Alright. Okay, so this is all for today. So again, if you have any more questions, always feel free to approach me or tutor. And thank you for your attention. Hope to see you next week again. Okay, bye.